going to be very basic policy. But the message is that there's really a lot of low-hanging fruit right now in these directions of political science, social choice, things and there are cycles that are involved. But I'll start with a quote. It's called the powerful tool in social choice. I like this quote. It's from yesterday. But I don't catch it now. It's actually not very necessary. The thing that caught my eye when you were synthesis is that one of the founders of mechanism design, which is the place where a lot of this stuff lives, the stuff of game theory, they're imagining totally exactly the same thing. It's not, there's not, and everybody knows. So topology does have a story. Now I want to briefly review it and then move away from it. This kind of topology is different from a lot of the approach to the problem. We heard about this stuff a couple of times yesterday, and I'm really glad that it did so. I'm sort of new to the whole story, and I'm not totally sure where the literature is and what the history of the subject is. I'm a little tentative when I was making these slides. I read the paper that I was thinking about getting the right picture, right? But I think that was confirmed yesterday in a couple of talks. So there's this, social choice theory basically deals with the following setup. We have a set of voters, E, and you have a set of candidates or alternatives or outcomes. Then L is just a set of preferences or rankings of the case. Linear order response. And then element of a vector of N2 and L is a profile, which puts in mind order ranking the candidates. And then if you have a function that's assigned to a profile are ranking social worker. If you just assign the winner of a single element, that's or an application. And then you can impose all kinds of requirements, restrictions on this function. And then you get the things like errors. Right? Or it requires unanimity in one of those forms. There's a state error, one of those forms that unanimity. Right, lower whatever they. So that's kind of the three standard setup. We don't need some standard solutions. I'm really just looking for in knowing that lots. But again, the whole thing is a logical version. That may, make a space of preference, and then just do the and then some really cool stuff happens there as well. It turns out that somehow contractibility of X is somehow the continuous version of the relevant alternatives X. So that was the topological story. Communists wouldn't find it terribly useful, right? Because just mathematicians like doing our cool abstract game. And then merge the two. In the time-honored tradition of putting the topology of this discrete set of linear equations. In a clever way, the way I understand it, I may be missing some details, but the topology is supposed to capture this independence of relevant alternatives. It's based on sort of pairwise preferences between two agents. All right. And I'll call this space, you take the channel recovery, you take its nerve, and this gives you a simplicial complex. Right? And then you come topology on this, and with very kind of bread and butter topological tools, like looking at the homology of the spaces involved, Berkeley actually recovers Arrow's theorem by applying this topological setup of changes. And then there's a lot of cool work since then. We actually heard about a couple of these things yesterday. The latter to the combinatorial topology proof of Arrow's theorem, which is sort of less algebraic topology machinery, but in the spirit of version of. And we also heard about the topological proof of the Hilbert-Sadler theorem, which is like Arrow and Hilbert-Sadler are these two like crowning achievements of social choice theory. In fact, if you talk to social choice theorists, I think they think Hilbert-Sadler is sort of like the deeper and more important. It says that there's no non-manipulable range of choice voting method or social benefit. All right, so like I said, underlying this is the fact that you're turning the discrete problem into kind of a continuous problem by choosing cleverly the color of your discrete set, right? And then taking the nerve and hoping that the simplicial complex that arises from this nerve captures some of the tone. And for those of you who know TDA, right, which we'll hear about a lot over the course of the rest of the week, this is a picture stolen from a TDA paper, right? Because this is exactly what happens in TDA, right? You have this discrete data cloud and you cover it in an interesting way, or you produce a family of cover and it's called persistent homology. So that's one way, right? Producing this covering your discrete set, producing this simplicial complex is one of the approaches, right? And like I said, TDA is a current sort of a glory of this approach in the last 15, 20 years. But there's a different way. It's actually a lot more simple-minded. You can just you have a discrete set, you can decide that these are going to be the vertices in some kind of simplicial complex, right? And that's actually been proved to be really fruitful as well. The idea is you're observing some objects interacting in some way. And if they're interacting, just make them be the vertices of a simplex in simplicial complex. In fact, in this session, the sort of little description of what this session is about is precisely this. Object interacting, this gives you some kind of a relational structure, usually captured by a simplicial complex. And there's lots of things that this applies to, and we'll hear about a lot of these things actually, and how we're doing in this conference. All right, so let me just remind you, again, this is for those of you who are not from this world of combinatorial topology, really I just want to establish some terminology. So a lot of what I'm doing here is dictionary, right? I'm going to take the standard topological dictionary of simplicial complexes, basic algebraic topology. I'm just going to try to look for, a corresponding thing in sort of social choice theory, political science. It's really very, very simple-minded, right? So a simplex is just a bunch of subsets of a set of vertices with the requirement that if there is a subset in the simplicial complex, it has to be closure on their subset, right? All the subsets of the subset have to be in there. So if that's my set of vertices, then my delta, right, a set of subsets, if I have to have those vertices in it as well, that's a requirement. But if I throw in another subset like U0, 1, 2, 3, then I'm forced to put in all that subsets in. If I throw in 3, 4, 5, 6, I'm forced to throw in all. So this is a purely combinatorial definition. That's it. That's the definition. exciting. One technical thing is that if since delta already contains the vertices, you don't really need to mention B. So sort of delta is identified with K. So that's what I'll. All right, but of course the geometric realization of this combinatorial definition, where you identify simplices with triangles and their generalization. So a zero simplex is a vertex, one simplex is a line segment, two simplex is a triangle, and so on. So an n simplex is just convex hollow and plus one in some sufficiently large Euclidean space where it can fit. So this example that was pure sort of from the torus turns into a picture like this. So this should be familiar to everyone. Then there's some terminology, I'll just need it later. So subsets are faces, subsets of each of the simplices are faces. Dimension of the simplex is one less than cardinality, right? The tetrahedron is a three simplex, a three-dimensional simplex, triangle is a two simplex. And the dimension of the entire complex is the highest dimension that you see in the. Now, of course, one dimension complex is a graph, right? So I like to know in my graph theorist colleagues where I work, but it's just they're just a special case of very boring case of what we do. They don't like it. And then we have a maximum simplex. That's a simplex that's not a face of anything else. And then this is slightly less standard terminology. A vertex is dominated by another vertex if the second one knows everything about the maximal simplicity that the first one is. So for example, V0 here, V0 and V1 and V2 are both dominated by the V3 belongs to the same maximal simplicity that all the other speak. Right? So the idea is a vertex that dominates another one knows more about this, has carrying more information. And the star of a vertex is just everything that emanates from all the faces that it is a vertex. So a deletion of a vertex is when you remove its star, right? But the deletion of a dominated vertex is called an elementary strong collapse. It's an important construction in sort of simplicial topology. And when you have a sequence of these things, it's called a strong collapse. It's relation to, you might have heard of the notion of contiguity that's related to it. Now, this is not, let me give you a picture of this. Here's a sequence of elementary collapses where V0 is removed first, so the stars are removed, so the triangle stays. V1, V2, V3 stays there. Then you remove, the order doesn't really matter. Then you remove V1, leaves you with the edge. You remove V1, doesn't move the star, but it leaves the edge, and so on. I don't know what happens next. Next, we remove, I guess, remove V2 here, then remove the edge, etc. So if you move that down to something that's called the core of simplicial. And it looks a lot like a homotopy equivalence, but it's not quite. It's actually a stronger thing than homotopy equivalence. Yes, the beginning simplicial terms and the last one are homotopy equivalent to each other. This is not generally the case. I think examples like the dunce hat or something like standard triangulation of the dunce hat, which is dunce hat's contractible, but it's not. You can't get it down to a point via elementary collapses. I think that's okay. Now, so we've heard also yesterday about maps in simplicial complexes. Simplicial maps that carry simplicities to simplicities. I don't need to use that, but I will just say that the set of simplicial complexes along with simplicial maps forms a category. It's a really nice category. So you can do a lot of this work, but in the abstract kind of category theoretic setting, and then see what it buys you over on the political side, which you'll see in a second. So among the standard kind of category theoretic constructions that you can do in simplicial complexes, there are things like pull-outs, push-outs, fibers, etc. Right? So I'll just single out a few. So a push-out or a colon is really you take two simplices, and if they have a common subsimplex, you glue them along that common subsimplex. Right? The special case that's familiar is when the common subcomplex is a point, in which case you get a wedge of simplicial complexes. That's also a standard construction category of logical spaces as well. You pick a distinguished, like a base point in each of the two spaces, and you just identify them, and glue the two spaces along their base. In this picture, these two disjoint simplicial complexes have been glued along that part. So that's that's the push out along the point. There's also the join, right, which is for simplicial complexes, basically just like throw in all the simplices of both complexes, and then throw all the simplices you can create out of the simplices of one and the simplices of the other. So logically, if you take the join of two spaces, it's kind of the space of all line segments between the two topological spaces. But that has a special case as well. When one of the simplicial complexes or spaces is a point, you get the cone over the logical space. What's happening there, the picture on the right, there's this cone point L, and to do a cone on K, you basically just form all possible simplices that have L as the vertex, and also use the existing simplices of K. So you cone out. Okay. If your L is 2 points, you also get suspension of in category of spaces or simplicial complexes. Let's go with the homology. Homology is the sum term from the category of spaces or category of simplicial complexes to deal in groups or graded rings or something like that. We don't need to know the definition of it. I just want to know that for simplicial complexes, this is actually particularly, I don't know, easy maybe the wrong word, but computable. It's the boundaries homomorphisms in the chain complex that determine the homology are given by their action on the vertices. So it makes it so that you can actually calculate these things. You can program a computer to do it, right? It's basically linear algebra. So it's always useful to take a space and try to make it homotopy equivalent to a simplicial complex, because then you can calculate a homology of a simplicial complex a lot easier. Homology just captures holes or voids, right? Again, those of you who know TDA, basically it's all about H0 and H1, right? H0 is the number of components, H1 is the number of sort of circular holes, right? So the torus has two non-homotopic circular holes, one this way, one that way, and it has one big two-dimensional hole from the middle of it. That's why the second homology of the torus is rank 1. These betas are Betty numbers, right? That tell you just the rank of the homology groups in any dimension. All right. So that's kind of bread and butter algebraic topology. Anytime, our conversations in the algebraic topology world started like, oh, I have a space, and then the person's like, let's calculate its homology. It's like the first thing we want to do. Okay. So that's just some of the things that one could do for simplicial complex work. So now let's switch over to the other side of this. So suppose I have in political science and social theory called agents, right? We mentioned this word before. So you can think of these as voters, political parties, jurors, members of a committee, anything, right? Any group of agents that's trying to make a decision on something. And we're going to say a subset of these agents is feasible or viable. This is not my terminology. It's also standard social truth theory. If if they're compatible in some way. This depends on the context. So you're supposed to imagine maybe a group of people who are willing to form a coalition and vote the same way on an issue, right? They're willing to negotiate. Right? They're willing to kind of function as a subunit. Here's the definition from a few years ago that a political structure is a set of agents along with a collection of these viable subsets, viable configurations, right? So the subsets of people that are willing to talk to each other, right? And there's a requirement is, you know, a bunch of people are willing to enter a coalition. The assumption is that any fewer of them would also enter a coalition, right? I take issue with the second assumption. It's not natural, but for now, let's just go, right? But look, if you make a definition like this, all you've done is you've defined this social complex. Right? That's it. That's the end of it, basically. Right? So, you know, you can try to like map out simplicial complexes for various situations. This is a picture that's pre-October, so it probably should be updated. But this is the kind of a thing you might want. So I created one of these pictures, well, sort of in the abstract sense, for the Bosnian parliament. So I come from Bosnia, which is politically like one of the most messed up countries in the world, which makes it horrible for people who live there, but fantastic for us who want to do like research on it. Okay, so there are these notions of viability and stability in social choice theory that go something along the lines of an agent is considered to be more viable if they belong to more coalitions, right? So this is really a question about an agent belonging to being a vertex of a bunch of simplicities, right? And then also the notion of stability of the entire political structure, depending on how many coalitions are there in it, right? So people in political science do think about these things, but certainly not from this geometric point of view. If you think about these notions in the world of simplicial complexes, you can very quickly define it in terms of star and the number of simplicities, right? So all that's happening here is like, oh, look, this is again very simple-minded. We're going to define the viability of an agent to be basically the size of its star, right? The size of the number of simplicities it belongs to, the number of coalitions it's willing to be in. Everything else in that formula is just normalization to make this thing be between 0 and 1. And the stability of the entire political structure is really just this like sum of the F vector, I think it's called, like this, just the sum of all the simplicities that it has, again, normalized. Okay. And the people in social choice theory that I've shown this to, they love it. And I'm just like, okay, great, that's fantastic. Let's do more. Right? Again, there's a lot of low-hanging fruit. So it's a full simplex, right? Well, with all, which means that all the coalitions are possible, right? A full simplex should have stability in one. So you can think of a simplicial complex, or you can think of a political structure that where some agents are not compatible as starting with a full simplex on this many agents, from k+1 agents, and removing some of the bits, right? This gives you a genuine sort of interesting, very interesting simplicial complex. You just remove coalitions that are not feasible. And of course, a discrete set, when nobody's talking to anybody else, has stability 0. And then you can, again, play this game, like what would a wedge mean? Well, the wedge is kind of a merging of political structures, right? There's an agent, there are agents in 2 political structures that are willing to form a coalition. They bring the political structures together, right? And then it's not hard to show that stability of the political structure increases as you do this. Forming a cone can be interpreted as introducing a mediator into the political structure. And it's also not hard to show that stability increases, stability of political structure increases when you do this. You can also introduce mediators into substructures. You can, later I might say something about this, you might you know, homology, having homology means that there's some kind of invisibility, some kind of political problem with the structure. You can try to cap off homology class, hone it off with a mediator. And of course, you can do this for not just, you know, you can do push out and join, meaning not just push out and joins on a point, but along substructures, more complicated. You can also talk about weighted complexes. Usually there are sets of issues that a political, you know, a system of agents is discussing, so you can label a simplicity with the number of issues that those agents agree on. For those of you who know about signal processing, this is what this is starting to look like. Simplicial complex with labels is a signal, basically. So all that this means is that, you know, these two agents, A0 and A2, agree on two issues, all three of them agree on one issue, etc. What this doesn't tell you is which issues they agree. So a better thing would be to add a vector that tells you which issues they agree on. Right? So that's really a signal process. Or you can attach a vector space to each one of these things. I'll say something about this in a second. So you just define corresponding notions of viability and stability for weighted simplicity. And everything really goes through the same. So distribution of power and relinquishment of power is another important topic to policy world and social choice. So often an agent looks to a better positioned agent for guidance, for action, and in fact, you know, might relinquish his power completely, vote exactly the way that agent votes. That's there's the notion of centrality captured there in political science. So the agent is more central than another one if every maximal viable configuration that contains one complete. But that's exactly, you know, the domination in the world of. So relinquishing power is really like having this elementary collapse. So this is called friendly delegation. And this is the same picture I had before, but now we're looking at it a little differently, right? It's like agents in succession being willing to, you know, give up their power to someone else. And the question becomes, who are sort of the most powerful agents? That's that core, the triangle, last triangle core of the play. Then there's a very simple way to interpret what homology means in terms of this. To have a homology class, to have a cycle that doesn't bound, just means you have a certain number of agents forming a whole, right? So, you know, to have an n-dimensional whole, you need n plus 2 agents to do it. So this is just saying there exists n plus 2 agents for every non-zero Benny number in dimension n. You have n plus 2 agents who are not willing to form a coalition, right? So your core cannot be a single agent, and you know, there's also the weighted version of that. So homology has a very simple interpretation. Right, and interesting, the question becomes, what are the minimal sort of cycles? Who are the most problematic agents, right? And try to cap those off with mediators. All right, let me just see how I'm doing. Let me just skip the setup of simple voting games. I'm switching gears a little bit just to tell you about one more thing you could do on these political structures. But let me just switch to the following thing. Let me just say that, you know, there's what's studied a lot in social choice theory are these power indices, quantification of powers. So often the context of that you see that is in weighted voting games, which are an example of simple games. So all of that means is that you have voters or agents, but their vote carries a certain weight, right? They don't have, it's not one person, one vote, right? And you see this a lot. So for example, the U.S. Electoral College is really a weighted voting, right? Each state are 51 players, right? Each state is a player plus the from Columbia, and they each have a different number of electoral votes. So they're different weights. So California has a player of weight 54. Massachusetts around from the player of weight 11. Right? UN Security Council is a standard example because you have these 5 permanent members that veto power. That turns out can be represented as a weighted vote. Anytime you have any like a board of directors or any parliament that has more than 2 parties, right? In the weighted voting, you assume that all the members of the same party will vote the same way. So you can think of each party as carrying different weight in the parliament. Board of directors vote, their vote is proportional to the number of shares they own, for example, right? So this is a standard thing. But what all this what all these standard power index calculations do or setups do, they assume that any coalition is possible. So what a power index is trying to capture is the ability of an agent to affect the outcome of an election, right? So typically what you have is everybody has certain weights and there's a quota that has to be surpassed in order for like a resolution to pass or from, something to change from status quo. Right, so U.S. Electoral College, the quota is 270. You have to gather 270 Electoral College votes to become president of the United States, right? So the quota is 270. And the question is, how many possible coalitions are there that will get you to 270, right? And if you are a voter that enters a coalition and turns it from a losing coalition to a winning coalition, that's like one check mark for you. So when you tally up all the ways in which you can be decisive in an election through all possible coalitions, that's basically a power index. So the details vary from index to index. The 2 most famous ones I'll mention in a second are Banzhaf's index and Shapley-Shubik index. And Shapley-Shubik just considers sequential coalitions where agents join in sequence, whereas Banzhaf just considers any subset without order, right? But all of these things assume that a priori, there are a priori measures of power. They assume that any coalition is possible, right? And that's kind of ridiculous, right? So a simplicial complex is a better way to model the situation. So what this simplicial complex is showing us is that there are some coalitions as determined by simplicities, and the vertices carry a weight on them. That is the voting weight of each of you. And the weight on every simplex is really just the sum of the weight of the vertices, right? So the coalition, so this says that this agent, I didn't label the agents with A0, A1, but this agent and this agent are willing to enter a coalition as represented by this edge, and their voting weight combined is 4, right? And if these 3 agents are in a coalition, their voting weight is 1 plus 2 plus 3, and hence the 6. Right? But you don't see an edge between this agent and that agent, right? That means they are not willing to enter a coalition. Okay? So you don't have this in the calculation of these power indices. And that really changes the story. So there are formulas based on sort of topological consideration, kind of modeling the homology calculation of the simplicial complex that we came up with, and wrote a little Python code to go along with it, because it's just fun, right? Now there are others who have considered, infeasible coalitions in calculations of power indices, but nothing like this from a point of view of topology. You're not supposed to understand, look through these formulas. The point is that they look ugly, but they're really just simple kind of counts of stars and things. So one application, for example, if you can look at and I'm really a little bit shocked that it doesn't seem like people have done this in the literature before. So you can calculate these power indices for each state in the US presidential elections, and that's standard calculation that was done decades ago, right? But what if you say, let's consider the blue states as a single voter, certain power add up all the electoral votes of the blue states, same for the red states, and then you have these swing states, and assume that this is really a simplicial complex situation in the sense that in any coalition, no coalition can have blue and red. So when you calculate these indices, so this is the Banzhaf index, middle column, Shapley-Shubik in the second column, you see that, and this is the part that's interesting. Florida, Pennsylvania, and Ohio all have more power than all the red states combined. Somehow in this setup. And you might say, well, Shapley-Shubik must be better because it kind of corrects it, but it's not. Shapley-Shubik is about agents joining coalitions one at a time, which can model like most of these setups. Like I see that, oh, the two of you are in a coalition, I like you, so maybe I'll join it, right? So it depends on who's already there. My decision might depend on who's already there. But that's not how we vote in presidential elections, right? We all vote at the same time. My vote, the way Massachusetts votes, doesn't depend on how Arizona votes. It's not sequential, it's really more subset, which is middle column, the Banzhaf set. So that's kind of interesting. And we did this analysis of the Bosnian parliament again, because it's fun, and I sort of wrote an article about this in a Bosnian, some Bosnian newspaper or something, and I got calls from these, political parties to like explain this to them. Like I explain it to you, and then they try to hire me, but So the point is that we calculated the power indices, but we're really trying to understand what the coalitional structure in Bosnian parliament means. So sometimes you have parties that will vote together, sometimes they don't, depends on the issue. So we kind of bring in the probability of them voting together, and it's kind of complicated. Of course, it's all like corrupt and manipulated, but whatever. We came up with some interesting. All right. So let me just quickly say that reflect back on this assumption that if you have a coalition, then the assumption is any subset of it is also going to form a coalition. Well, that's not really realistic. Maybe I'm in a coalition only because you are, right? If one of you leaves, maybe I no longer want to be in a coalition. So a better way to model all this is hypergraphs. So hypergraphs are precisely that they just eliminate the requirement of closure under subset. So hypergraphs are something that graph theorists have studied a bunch, and now like data scientists, but I don't think it's been explored from the topology point of view as much. So a hypergraph, typically it's represented by blobs, right? So like this means that V0 and V1 are an edge or hyper edge, they call it. And then this big blob means that V0, V1, and V2 are also a hyper edge. But from us, when you know about geometric realization of simplicial complexes, you really want to draw this as a simplicial complex. And the way you draw it is just add simplicial complex, but missing some faces, right? So you don't see the face V0, V2 here because there is no edge V0. So what this says, for example, is that the agent V0 leaves. So there is a coalition with the three agents, right? But if V0 leaves, the coalition falls apart. V1 and V2 will not stay. Because there is no edge. So simplicial complexes are examples of hypergraphs. And again, this is sort of like a simplicial complex that removes some of its phases together. So you can read or sort of try to play the same game, and things like its viability and stability and all this stuff carries through. But now it actually has an interesting connection to things in hypergraph theory that are not present in simplicial complexes. Things like these clustering coefficients. It turns out clustering coefficients really are capture the sort of notions of viability. There's also a better homology theory that I think might be more useful than the standard way to compute homology of the hypergraph. The homology of the hypergraph is kind of the way it's done now is kind of a cop-out. It's like take a hypergraph, complete it to a simplicial complex, knowing all the phases that are missing, and then how to do that. So do homology. So we're going to call that homology the homology of the original hypergraph. But you really destroyed a lot of information. So there's this new notion of embedded homology that I think does a better job of will at least be applicable to this kind of story. So for example, and this is embedded homology of this hypergraph, H0 is C2. So somehow this hypergraph actually has two connected components, which sort of makes sense. If you contract this edge, all you're left with is kind of two vertices. The middle open triangle sort of disappears and appears to place. I'm not totally sure I think about it, but if you were to close that up into a genuine simplicial complex, you would just get one component. So I think there's a lot to do here with hypergraphs and this story. Okay, so let me just spend a few minutes. I'm not go over time on 45 minutes. Just like all the possible places this could go, right? So I mentioned signal processing. So you could kind of do this Fourier transform of a signal, the Hodge decomposition of a signal, to sort of get some sense, some more intuition about the interaction between the agents, right? You could actually associate a vector space to each of the agents that sort of can be regarded as an opinion space, right? Sort of their varying views on issues. And the inclusions of faces can be thought of as discourse. This is not, I'm doing this precisely from existing work on opinion dynamics by Hanson and Rex. I think this can be just redone in terms of sort of political interaction. Right? But then you have basically in the world of sheaves, the sheaf cohomology does capture a lot of this interaction for vector spaces or simplicial complexes. There's, like I mentioned, there's a category of simplicial complexes. That's a standard thing. You also have corresponding, you can call it a political structure, right? And what might that mean, right? So it might sort of tell you about agents merging, or there's a turmoil, new parties are arriving, parties are being consolidated. All of these things can happen in the simplicial method. And you automatically, just because really you just change the language, you have this automatic equivalence of categories between category of political structures and category of simplicial complexes. So what about sort of category theory level stuff that can be imported into this? And there's evidence that this would work. I think entire social choice theory and game theory is kind of begging for this formalized approach. I think that's wide open and shouldn't be too bad. And there's evidence for this. So hypergraphs also form a category. You can start exploiting that immediately. But there's also this other work that relates. There's this work by Hans Keiding from the 80s that basically error and Euclid's after create just like these crowning achievements of social choice theory. They're just corollaries of what's called the innate element. Innate element is a fundamental result in category theory that sort of like lets you study categories. Sort of like, if you want to study rings, sometimes it's better to study modules of rings. That's exactly what this is. This Unanimous said, instead of studying the category, you might study functors from it to sets. So it turns out the innate lemma just contains both these things. So that's really sort of intriguing. And a student of mine is just redoing this for the Volić-Young theorem. Volić-Young theorem is a theorem that says there's no good apportionment method. You can't sort of apportion legislative seats in a way that will satisfy certain basic assumptions. So she's able to sort of kind of do it in categories. So I think that's something to be pursued. A lot of this power index story includes probability. So probability distributions that tell you like how likely certain coalitions are. That's tied to sort of where you are in the simplex. So the simplex, it's again like, you have a coalition and then you like slap a simplex to represent it. But a simplex is more than just, vertices interacting. Maybe the place you are in the simplex can tell you something about the influence of certain agents in that college. You can have this parameter like the alphas that, parameters alpha can tell you something about the dynamics within each college. You can also talk about, things changing over time. There are kind of evolutionary models for these things that's been done already. This thing called growing weighted complexes. And then like you can just talk about, like pick up a book on simplicial complexes and say like, oh, what is this? This translated into anything interesting over in the, political. Thank you.
Any questions? Yeah.
There was very containing like 2 points, and they were like a simple containing those points and a link of string. But the grades like emphasizing that point in the circle or the string.
I'm not sure, I can't quite see your picture, but the circles are heads for simplicial complexes.
But the
Interaction.
right.
So the edge here, so they don't, yeah, I have two different kinds of pictures, because I was lazy. So my second set of little pictures, it had edges like this, but it should have been blobs around to each of the two birds. So really the way graphs here, they don't draw edges, they just draw blobs around subsets of vertices to indicate hyperedge. But in some of my pictures, I had edges, but every edge that you see in my
Grades like containing the grades above underneath.
building. Yeah, the vertices are automatic, yeah. Their vertices are automatically edges, right? And yeah, and you need alpha, beta, gamma as well. I can talk more about it. And also, I don't really know much about Africa. This plan. Yeah.
In simplicial complexes, like interesting structures are holes. But in hypergraphs, we have another interesting structure that are hyperedges that do not have skin, without skin. It's kind of a coefficient that we only form, for example, if 1, 2, and 3 are present. But you don't have any skin, you don't have the
No faces of the kind, right?
and not even vertices in some senses.
Right.
Does that have a name? Have you seen something like that?
Over in Bolivia, no, I don't know.
And is there some construction, some topological construction to identify them, these skinless algorithms?
No, not that I know. To me, it's just like an open sequence or something, right? But yeah, I'm not sure over in the political science world.
Because that would be like an additional interesting structure that is happening in hypergraphs but are missing in each other.
Absolutely, sure, right. Like these agents only come together because they both come together, right? Otherwise, it falls apart.
And they are very fragile in the sense that if you without any of the
It all falls apart, sure. Yeah, absolutely. That's exactly it. No, I don't have any vision, but thank you for, because The simplicial complex is, I guess, too complicated. It has at least like 12 vertices or something. So, but that, yeah, that's, but it would be nice to, yeah, no, I we just calculated this and that's it. It would be nice to know the topology of it, like calculated homology. It's actually a really good, it never occurred to me. I was just so flabbergasted with the numbers themselves that I was like, not that been listening. But yeah, that's actually good.
What about other topological, algebraic topological constructors such as fundamental group or other homotopy groups such as?
Yeah, exactly. Right. I mean, I haven't gone past homology because it seems that you can actually calculate it, but yeah, I'm sure people like, really have who've been in this topological social choice world more and really got their theory with this model would know. Yeah, I don't know about homotopy groups. Taiwan, of course, a lot of these things are, a lot of the, you can calculate Taiwan, but it often turns out to be abelian, so it's really the same as H1, so it doesn't get you more. So, but I don't know what a type 2 and higher.
Is there any interest for vibrations? When you were mentioning like adding the
Yeah.
vector spaces.
That's sort of my next, like, I grew up on sort of diagrams of spaces and kind of looked up fibers and iterated fibers and push-ups and pull-backs. So that's like my natural go-to place, but that's what I was thinking next, yeah. Okay.
Can I offer a guess as to the power of the red states?
Please.
Is it possible that the swing states win on their own without the red
No.
states?
No,
They don't have enough.
they don't have enough, yeah.
But the red states have, or the swing states, I think are more needed by the red states than the blue states. And so therefore they show up as kind of the minimum.
Yeah, sure, yeah, that makes, blue states combined have more electrodes than red. But you're right. Yeah, exactly. But still to me, it's so shocking that these three states would have more than all, and they were closer, so let's still expect red states to have more, but it's not. It's not the case, it's really the fact.
So this isn't a math question, but what should voters take away from this?
That they should not vote for Trump. What should the voters think? From this particular thing. I have another book that's coming out in April that's for the voters. And what they should take away from that is that we should do ranked choice voting, we should do voter representation, we shouldn't have single member districts, we should eliminate the electoral college. I can't vote.
I was wondering in distributed computing, we have simplicial complex models, as you know, and we also recently, for some reasons dealing with the district logics, we have planned, so we considered also anti-graph forms, but in between we sort of considered also simplicial sets.
Yes, I saw it in one of your papers, that's right, that's a good bridge to sort of space, generate spaces, yeah.
But I mean, it has advantages with respect to the topological space kind of models, but that makes sense in terms of conditions. But I mean, there's some sort of funny things going on.
Right, but you consider semi-simplicial sets also, right? So I was sort of thinking about what might it mean to add the degeneracy then. And I wasn't question. I meant to think about it. I think it's really interesting. So I don't have a good answer, but I'm very. When Adrian's do what? Yeah, but I think it's, this dynamic of growing simulation complex. I don't know much about it, but I know there's work on this, like evolutionary model Yeah, again, that's one of the things that I think will be. Really interesting to look at. Yeah, absolutely. I don't know. About it.
So I have actually a follow-up question on that one, because you mentioned the touch theory and signal processing, and that's has been used mostly for, at least as far as I know, for average consensus, for instance, in IoT, trying to converge with some common value. And would that mean something like look at the way to sort of converge?
Right, so the convergence is right of yeah, of the hardware competition. I don't know, it would mean, yeah, I don't know what it would mean. Well, but better chance of consensus or something. Yeah, that's a good, yeah. Yeah. If I threw all these things out there, I really, I just don't feel like they hold promise, but unfortunately, yeah. That should.
So are you aware of the applications, let's say the communication systems, manipulation of information, influencing voters dynamically? Fake news, real news.
Right. No, not really. I think this sort of opinion dynamics sheet over Simplicial complex, I think that might hold some promise in that regard, but I'm not aware of. There's, like Simplicial complexes yet being used to model.
Sounds like a business opportunity.
Yeah, well, like I said, I could have had, in Bosnia, I had a business opportunity.
Thanks.